Good morning, guys. So let's have one example of um, a problem regarding the determination of the center of rigidity and center of mass of an irregular structure here. So basically, we have this floor plan, the second floor plan, which is given, and we are just asked to determine the center of rigidity and center of mass on this second floor. Okay, so the columns are actually given in terms of their size. So C1 here are all 40 by 40 centimeter, and C2, which is actually this column here, is 0.30 by 0.50 meters. No, see, so the dimension is actually shown here. So this is 0.3 and this is 0.5. So it's important to note the direction of the dimension in case the columns are not a square column, because that will be a key to the determination of its flexural rigidity or simply the moment of inertia. Okay, so the beams are all 0.30 and 0.5 meter deep, and the slab thickness is 0.10, which simply means that the mass of the entire area is actually distributed fairly and uniformly all throughout the slab system. And there's an opening here which is, I think, used for the purpose of a stair access from the ground to the second floor. And there's also a shear wall here which is 0.40 meters thick and 6.5 meters long. Okay, so the elevation or sectional view of the frame is actually given here, and our focus is actually on the ground and the second floor, since this is the uh, the part in which the second floor properties are actually considered, and also this um, part in which the lateral force resisting columns are actually um, resisting the forces. So this is the ground story that is now in question. So for the solution of the center of mass, or we can abbreviate it as CM, we first assume that the mass, of course, is uniformly distributed on the entire second floor area. And note that if we consider three areas, one big rectangle and two negative areas to account for the opening and the projected area from the re-entrant corner, we can actually um, evaluate or solve for the center of mass on the basis of Varignon's theorem here. So this is now actually looking into we're now actually looking into a scenario wherein uh, this whole floor is actually considered a positive area, and this re-entrant part here is a negative area, including the opening here. Okay, so let me first set up my tablet so that I can use the pen. Okay, so we have now here the whole triangle, the whole rectangle that I'm referring to is the big rectangle, which constitute my first area. Okay, and I have here a small rectangle that constitute the opening, and a small uh, square here or rectangle that constitute my uh, re-entrant corner. Okay, so I have to subtract these two areas here in order for me to get the center of mass. Okay, so I don't know where the center of mass is actually located. So let's now try to solve for the areas. Okay, so this is okay. So the big area here is actually 18 by 12. This is now the big rectangle. Okay, so this is the big rectangle here. And this small rectangle here is the re-entrant corner. And another here is the stair access. Okay, so these are both negative areas because we are subtracting it. And taking a look at the values of your moment arms, x1. So the reference of the moment arm is actually from the bottom left corner. So let's specify now the reference origin. So I think my reference here for my origin is located somewhere here. Okay, so if I'm going to solve for the x's are the centroids of this okay rectangle. Okay, so these are the x's. So x here is actually this distance. Okay, x here is this distance here, and x here is this distance over here. Okay, so these I think are plainly very easy to solve. So this is actually 3 meters, this is I think 9, and this is simply 6 plus 3, or 12 plus 3 is 15. Okay, so if I'm going to use the y now, the y values, my y here is again 3, my y here is somewhere 6 meters, and my y value here is 6 plus 3 is 9. Okay, so this is referred to this as my origin. Okay, so if you want to refer it from another reference, you may do it. Okay, so this is 9, 3, and 16.5. Okay, so that's 12 plus 3 is 15 plus 1.5. Okay, so my correct here is this 15 point, no, it's not 15, but this is 12 plus 3 plus 1.5. Okay, so it's 12 plus 3 plus 1.5, so this is a 16.5. Okay, and for y it's 6, 3, and 9. Okay, so all we have to do now is to make use of Varignon's theorem. Summing up forces or area Okay, area multiplied by the x's divided by 80 gives you your xm. Okay, and the area multiplied by yi over 80 gives you the yms. Okay, so the total area here, of course, you can simply add or subtract these two from 216, you get 162, and then multiply this and x1 plus this minus this plus x2 minus this plus x3, you get here 9.5, and ym is 216 times 6 minus 36 times 3 minus 18 times 9 gives you 6.333. So these are now the coordinates of your center of mass, which is at 9.5 and 6.333. Okay. Okay, for the center of rigidity, we only consider, of course, the lateral uh, force resisting elements or system, only the columns and the shear wall. So the columns at the second floor, of course, C2 is not included because it's not the part of the LFRS, or yes, okay. So what I mean is, in this particular case, this column here are not actually a part of the uh, lateral force resisting elements of this second floor, because this second floor is only holding up to is held up by these columns here. Okay, so E is of course given, it's 2.5 times 10 to the 7, and if we compute for the moment of inertia of the columns of C1, it's simply 112 over 112 of BH cube, so this is 0.4 cube over 12, and L is 4.5, so you might as well want to make use of the rigidity in terms of 12 EI over L cube. Okay. Okay, so for the absolute rigidity of the shear wall, we have here your Ix, which is 0.4 times 6.5 cube divided by 12, and for your Iy you have a 0.4 cube 6.5 divided by 12. Okay, so if you are going to look at the shear wall now, my shear wall is actually directed in this manner. So this is the 6.5, and this is the 0.40 dimension, and if you take a look at the earthquake rigidity along the x direction, so if you look into this direction, my Ix will be definitely referred to this axis. Okay, so this is my B, and then this is my H. Okay, so if I'm looking towards this direction, my B will be 6.5 and my H will be 0.4. Okay, so take a look at how the orientation of this Ix and Iy are placed here. So Ix meaning to say that your moment of inertia, this is along the x direction. and IY simply means that this is along the Y direction. Okay, such that your R2X and R2Y now for your shear wall is simply 12 EI X over L cubed and 12 EI Y over L cubed. Okay, so we can now define the matrix of rigidity and distances, or you can use a table in case you don't want to use matrix analysis here. Okay, so this is now a table that you can make use of, or a vector or matrix. So these are the R1s. Okay, so this is for column 1, column 2, column 3, column 4, column 5, column 6, column 7, column 8, column 9, and then the shear wall. Okay. Okay, for your axis, all the columns from 1 to 2 here have x equals 0 as your as your distance. Take a look. This is 1 and 2 columns. Column 1 and column 2 here have 0 on the x direction. Column 3 and column 4 and column 5 have 6. Column 6 and column 7 has 12, and 8 and 9 has 18. Okay, so those are the x's, while the y's for column 1, column 3, column 3 and column 6 have 0, including column 8, and then column 1 for 9 has 6. Column 7 has 6 minus 0.5. Okay, and then column 2, 5, and that's column 2 and column 5 has 12, while the shear wall has also 12. Okay, so those are the distances that we are actually referring to this as x. Okay, so this is 0, 0, 6, 6, 6, 12, 12, 18, 18, and then 15. And then for y, it's 6, 12, 0, 6, 12, 0, 5.5, 0, 6, 12. So the center of rigidity is therefore computed on the basis of the formula. XR is summation from I equals 1 to 10 of your R xi's times xi's. Okay, so you simply divide this summation to your summation of R xi's, you get 14.987, and YR is equal to summation from I equals 1 to 10 of RYI times YL over summation of RYI's. You get 9.604, and this defines now your center of rigidity CR, which is equivalent to 14.987 and 9.604. Okay, knowing now the center of mass and center of rigidity, we can finally calculate your eccentricity E. X and Y by simply subtracting your XR and XM, and for EY you simply subtract YR and YM, so you get 5.487 and 3.271. So let's try to roughly locate those values here. Okay, so these are this location of CM. It's actually 6.5 there, and then 9.5 here. That's the center of mass, and then we have here your 9.604 center of rigidity and 14.987. Okay, so So basically the eccentricity that we are referring to now is this one. So this is the EX, okay, and this is the EY, which is 6.487 and 3.7271. Okay, so where are we going to use this eccentricity? So remember that for regular structures, we have to compute for your torsional moment. Okay, so the torsional moment now is actually measured in terms of okay, the in terms of the torsional force, which is assumed to be 1. Okay, so your m t of x is simply equal to 1 times EY. Okay, so if we are actually going to compute for the torsional moment on the basis of 1 kilonewton force, shear force here. So this is your 1 kilonewton, and you have also a shear force here of 1 kilonewton. Okay, so your torsional moment on the direction x will be 1. Okay, so this is the x direction. Earthquake force on the x direction is 1 over EY, or simply 3.271. And for your MTY, you get 1 times EX, which is equivalent to 6.487. Okay, so I have here now another sample exercise, but I want you to do it by your own. So you just check your answers here. Okay, so we have here almost the same second floor plan. I just removed the shear wall, and I think everything is the same except that the shear wall is gone here. Okay, so there's no shear wall present, so you might as well remove 2, 4, 6, 8, 2, 4, 2, 4, 6, 8, 10, 11. Okay, so I just removed the shear wall. The shear wall is removed. Okay, so this 10 here was removed, but it was added a column 10 and a column 11 there. So two added columns, which are the same as C1. The same as C1 were added. Okay, so it's a 10 minus 1 plus 2. So all in all, we have 11 lateral force resisting system. Okay, so I want you to do this exercise, and the answer is already given. So please verify the result. Okay, so if there are questions, we can discuss it after this video. Thank you very much.